Yeah, okay. Right, so how to run CFD? First, you upload your CSM file like you build on your own computer using engineering sketchpad. And once you upload it, you get a surface mesh, right? How the surface of your airplane looks like. Then you're going to generate a volume mesh. So on both steps, you need to specify a few things. For example, when you're generating the surface mesh, you need to label the leading edges and the trailing edges. These are the most important things to label because the mesh has to be refined, extra refined along the leading edge and trailing edge. So let me show an example of this. So this is my CSM file, right? If I look at the airplane.csm file I generated, you can see that I did a few things. So this blend is when I generate my wing. Okay. After the blend, I select the edge. Basically, the edge selection works by providing a XYZ that's close to the center of this edge. Okay, so basically, the XYZ here is around the center of the leading edge, and I put a label, right? Put an attribute to this edge, and I say the edge name is called the leading edge. Similarly, there are two trailing edges because the trailing edge is blunt. Okay, the trailing edge works like the airfoil works like this. So there is a blunt trailing edge. So if you go through the leading edge and the trailing edges, there are actually two trailing edges, right? Make sense? Okay, so we put attributes on both trailing edges as the same trailing edge. Okay, then the next thing is we specify a few things on how do we actually generate this mesh. Can you see it? Maybe it's dark. Okay, better, right? So we set the leading edge, which is the edge name over here, to having a first layer thickness of 0.001. So this essentially tells that the leading edge has to be refined in the direction normal to the leading edge. Okay, so if you think about a wing that's extruded along this leading edge and trailing edge, that means this first layer, so the mesh is additionally refined in this direction, right? In the direction that resolves the curvature. And the thickness here is 0.001. Right. So in your CFD calculation, it's best to set this first layer thickness to be a small fraction, let's say 10% of the leading edge radius, so that you're resolving the curvature of the leading edge well. So that's actually something pretty important to actually run a good CFD. Okay. If you don't get it in the first shot, then the run a simulation, it's pretty easy to identify that the leading edge is under-resolved, right? And I can always help you look into that. So once you start it running. All right. And yeah, so the other stuff, I think you can leave it as default max edge length. Max edge length is the maximum length of the edge on the surfaces. So that's a global parameter, and you can also set each face to have a different max edge length, right? So these are things you can control the fineness of the mesh. One thing to note here is that if your dimension of your mesh is different, you do need to change this, right? So if you have the dimension of the mesh being millimeters, for example, you don't want to leave this as 2 because 2 millimeters would be too small of a mesh. You would have a extremely fine mesh that would take forever. Okay, so basically remember the units. You might need to change them. All right.
So your 0.001 is meters right now?
Yeah, this is all in meters. Setting this as 2 is essentially saying that I don't care how big the mesh is, as long as we are resolving the curvatures correctly, right? 12 degrees being basically there is no mesh that's the curvature is resolved up to 12 degrees of any surface. All right, so basically the resulting mesh is something I think you've seen a lot in, right? You've seen a lot. So if you go to here, I think it's this airplane. So if you look at the mesh, if I do show mesh, and if you zoom in, right? So you are gonna see this is a little bit. You're gonna see that the leading edge is extra refined. I should maximize the window. Yeah, you're gonna see the leading edge is more refined than the rest, right? So you have more curvature resolution here. All right, it's a little bit hard to see this way, but and the trailing edge is also more resolved. Okay. Right, so that's generating surface mesh, and when generating the volume mesh, you need to provide yet another. So I'm going to send all these examples out. So this file controls the volume mesh generation, and first of all, you have a refinement factor, and actually ignore the sources. So I don't think you need to specify any sources for this. This case, and ignore these actuator disks. Yeah, so the only thing I think you need to specify is the only thing you need to change is the first layer thickness. So that again depends on the Reynolds number. You have to really figure out how thin your boundary layer is, especially in the leading edge, because that's where the thinnest the boundary layer would occur. Okay, and the way we have been kind of doing this when we were discussing laminar boundary layers, right? So first of all, you have to figure out the Reynolds number based on the leading edge radius of curvature. So let's say the Reynolds number based on the leading edge radius of curvature is going to be equal to rho u infinity, the radius of curvature at the leading edge divided by mu. Okay, and then the Reynolds number based on the boundary layer thickness here, which is defined as rho u infinity times the boundary layer thickness, is about the square root of the Reynolds number based on the leading edge radius of curvature. So this way, it's easy to estimate delta, right, based on the leading edge radius of curvature. And it's best to set the first layer thickness to be a small fraction of the delta, like 10% of it, so that you are actually resolving the boundary layer. So that's the only thing important to set in when you are generating the volume mesh. Okay, so essentially surface mesh, the leading edge and trailing edge, set it to resolve the radius of the leading edge, and the volume mesh, set the first layer thickness to resolve the boundary layers. That's the two most important things to set. Otherwise, you don't really need to change the default. All right, any questions?
So that delta is the thickness where?
That delta is the thickness on the surface of the mesh, like everywhere. On the so
okay, so that delta is not the thickness of the boundary layer. That's the first layer thickness of the mesh.
Of the mesh, yeah, that's right.
And then, sorry, your equivalency to root Reynolds number was what?
So the first layer thickness should be, let's say, 10% of the delta. Right, so essentially what you do is you have all these numbers, right? You compute a Reynolds number based on the leading edge radius of curvature. You take the square root, you get the Reynolds number with respect to the boundary layer thickness near the leading edge. Now you have this number, you also have this, right? So you know what delta is. Make sense?
And your square root, what function is that? Like, is that relationship something that I should recognize?
I think if you review our laminar boundary layer discussion, right, we did a dimensionality analysis saying that the thickness of as the boundary layer gets thinner and thinner, the effect of the viscous forces goes like the square, right, of the thickness. So that's, if you remember, there is one effect that makes the viscous forces larger. On the other hand, if you make it thinner, the volume of fluid affected by the viscous forces also decreases proportionally. So as a result of that, the thickness of the laminar boundary layer has a square effect, right, on its effect. So essentially that's where the square root comes from. Okay. Yeah, so I'll send out more detailed information later today as an announcement and also on Slack. All right. So once you have the volume mesh, you should be able to see it on this interface. And the next step is to you can launch a case specifying case name and a config file. So for the config file, you should actually see a lot of examples when you log in. I basically give you my account for teaching to do the CFD calculations. So in my account, you are going to see all the calculations I have done to show you during this course, right? So for example, all the subsonic and the supersonic calculations and some additional stuff is done over here. So these are the supersonic calculations. This is the Mach 2.4 calculations. You can see the results over here. And when you click the runtime parameters, and you can also copy that, right? That's all the stuff you have to specify when you launch a new case. So for example, free stream, you have the viscosity, and you have the Mach number, and the temperature, etc. So here the viscosity is in a solver unit, and the solver unit means that in the solver unit, the free stream speed of sound is equal to 1. Okay, so one solver unit in terms of speed gives you actually the free stream speed of sound. The solver unit for density is the free stream air density. Okay, with these two solver units, I think you can actually back out the solver unit of everything else. For example, the solver unit of viscosity, right, can be backed out from the fact that the Reynolds number is a non-dimensional quantity. Okay, so the Reynolds number, if you look at it, it contains density, right, which we know density equal to 1 in the solver unit is equal to the free stream density. Okay, velocity, we know a solver unit of equal to 1 in terms of velocity is the free stream speed of sound. And the length is whatever length your mesh is, right? One solver unit is 1 in your mesh, okay, whatever your mesh is like. So because this is non-dimensional, you know exactly what the solver unit of viscosity is. All right. So if you have trouble computing, for example, the viscosity in your solver unit, I can also help. All right, just Slack me, and I can help. And for example, this is actually pretty standard if your mesh unit is in meters. So if your mesh unit is in meters, roughly 10 to the minus 8 is going to be roughly the viscosity of air. All right. And you don't need to change the volume output and surface output, and the boundaries, you need to, there is a far field, and whatever boundaries you have in your CSM file needs to be specified over here. No slip wall is usually on the surface, and free stream is on the far field. I don't think you need to change anything in Navier-Stokes over. You don't need to change anything turbulence models over, and essentially you can use and I don't think you need to change anything time stepping. So you can essentially use some of my existing calculations as a template and launch your CFD calculation.